So the title of my course is Enumeration of Deregular Graphs, but that's a little lie, just to make it short. It's actually asymptotic enumeration. And we will not just look at deregular graphs, but graphs of a given degree sequence. So the main question is, given a sequence, D of n integers, how many graphs are there, labeled graphs, with exactly that degree sequence? So how many graphs G are there on vertex set n such that vertex I, or the degree in G of vertex I, is equal to di. Okay, and I'm saying here labeled graphs. I do not care about isomorphisms. So let me call the set of these graphs just G of D. Okay? So what I want to know is how big is that set? That's a set of all graphs with vertex set n and realizing that degree sequence. Okay, and as a special case, I will write G of n ordinary D for G of, well, the deregular sequence. Right? So, yeah. N components, each has size D, and that is just the set of all n vertex deregular graphs. So, right. I don't think I have to motivate much why you would be interested in counting these in this audience, but let me do so anyway. So one thing, why would we be interested in like pretty precise counts of like the number of graphs with a given degree sequence? Well, if we divide by n choose m, then this is exactly equal to the probability that the random graph G and M has degree sequence D. Yeah, and you might be interested, well, you might want to know pretty precise estimates for that probability. One paper where this has been used, or some of these enumeration results have been used, is called friendly bisections. By, well, let me not write the names of the random graph, by Ferber, Kwan, Narayanan, Sa, and Soni. So that's where you need really precise counts, like how many graphs are there with a given degree sequence. Okay, so that would be a motivation for us. There are also real-world motivations. So in a real world, let's say, like you look at a population and you do not want to look at a uniform random graph on this population, but rather you want to say, well, I want to know, like I know about my network that vertex 1 has exactly like few neighbors, vertex 2 has a lot of neighbors, like, and so I'm fixing my degrees of my random network. And now I want to model certain situations. You want to know how many networks are there with exactly that degree sequence, just in order, or like how does a random outcome look like when all the degrees are fixed. Okay, so that's my motivation. And now, well, what can we say about the number of deregular graphs? So let me start with actually some exact enumeration results. There aren't many that I can tell you. Okay, let's start easy. What is the number of one regular graphs on n vertices? That's a number of perfect matchings, right? So here n is even. That's a number of perfect matchings on n vertices, labeled perfect matchings. How many are there? Well, it is an n factorial over n over 2 factorial, and then a 2 to the n over 2. Why is that? Well, I mean, you can think of your n vertices like in order, and like look at any permutation, put edges here in like from I to I plus 1, right? And then just like that's the n factorial. And then you are overcounting some of these perfect matchings. Like you can swap all of these. That's the 2 to the n on 2. And you can also swap the pairs around. That gives you the same perfect matchings that the n over 2 factorial. There's also an exact formula for the number of 2 regular graphs. I'm not going to write it down because we won't need it anymore. But that is essentially the number of ways. So what's a 2 regular graph? Union of cycles, right? So it's the number of ways to partition n into cycles of length at least 3. Okay. Now, for larger d, there's no such exact formula known, no short one. So for g of n3, there exists a recurrence relation. And this was is one of the starting papers to look at that problem by Reed from 1958, I believe. And from this recurrence, you can like deduce an asymptotic formula. So you could say how many there are. And we will see a much more general formula later, so I'm not going to write it down now. And for g of n4, you also have a recurrence relation that was found by Reed and Wormold. But for this one, they didn't even bother to write out an asymptotic formula. So that is a lot more complicated. And then for d being constant and n tending to infinity, there is a proof that a recurrence relation exists by Gessel from the 1990. But that is a non-constructed proof. So it's not even a formula you can look at. Yeah. And then there are algorithms for constant t that approximate them. Like for small d and n, you can like write out some algorithms. But in general, like we don't know anything explicit. So naturally, you would like to know, well, what can I say? Like, do I have other methods? And that's where the asymptotic comes in. Okay. Okay. So the asymptotic, well, we have seen a lot of asymptotic enumeration in these courses. What I mean is a formula so that g and d, say, is equal to f, some f of nd, something easy to calculate, times 1 plus little o of 1, and this is as n tends to infinity. So n here tends to infinity. For d regular graphs, that statement is clear. For g of a d, what I want here is a function easy to calculate of my degree sequence d. And here, so when I say 1 plus little o of 1, I mean also as n tends to infinity. So technically, I am talking about a sequence of degree sequences. Okay. Good. Now, for this sort of problem, asymptotic enumeration of graphs by degree sequence, there exist completely different methods than what you have seen so far. So let me give you an overview. These are the methods. Then here is the range. And then here is the people, so who. Okay, so the first one is what's now called the configuration model. Okay, that one, well, Bolobash framed it, called it the configuration model, and the way it's explained today with probabilities, that's his invention. So from the 1980s, I think 83. Earlier versions like by Bender and Canfield. So they have an asymptotic formula for D being bigger of 1. And it's like a version of the configuration model, but talking about inclusion, exclusion, not about the probabilistic view. And the probabilistic view is really powerful, as what we will see today. So the probabilistic view gets you up to D and most D root 2 log n. Okay, so D is allowed to tend to infinity slowly. There are other people who worked before Bolobash. So it's Bekeshi, Komlosh for bipartite graphs or enumerating matrices with row and column sums. So that's equivalent to counting bipartite graphs when it's 0-1 matrices. Wormald worked on this in his PhD thesis, or they use a version of this configuration, but not with a probabilistic language. Then if you use the configuration model plus switchings, and we will see them in this course. So I'm not expecting you to know this because that will be the content of this course. But with switchings, that was invented by McKay, 1985. And that allows you to go to D to be little o of n to the 1/3, third root of n. Okay, and then more elaborate switchings allow to go to little o of 1 root n. That's McKay and Wormald in 1989. Okay, so that was like a super successful idea, and it worked for D being like quite large, like root of n, little over root n. Then there is let me wait with the second one, and let me go with the third one first, because this one works for D to be very large, so at the other end. And by very large, I mean at least n over log n. That uses an approach via generating functions. Generating functions. What do I have here? Cauchy's formula. And what's called the saddle point method. Now, if you have no idea what this is, that's okay. So like you express the number of D regular graphs as a coefficient of some multivariable function, and then you try to estimate complex valued integrals. So I'll try, yeah. Anyways, so that's by McKay and Wormald. Like a separate paper in also like the same time. I think it appeared 1991. Okay, so and then in between, we have a third method. Let me call this like recursive relations and contractive maps. And that works for D in between those two ranges. So it covers, let's say, n to the epsilon, at most D, at most epsilon times n. And that's myself and Wormald, relatively recently. Okay, now what I want to do in this course is to give you an overview of all these three methods. Okay, so we will see the configuration model, not with the switchings, but the original Bolobash proof. That's my goal for today. Then I want to spend most of the time with this method, because it does cover what the switchings can do, and it goes up all the way to linear n. This one is very analytical. I might give you some ideas what's going on. I'll definitely, probably won't go into details with this. Okay, and I should say, yeah, those are the ranges for deregular. All of these methods generalize to irregular sequences, and we will see precisely what they say in each of the parts. So this one becomes a bound in terms of the maximum degree, and for these two, you want your degree sequence D to be nearly regular. So I want that all the DIs are around this average D in some way that I'll make precise later. Okay, and you might notice that none of these methods is like anything you've seen in the first few weeks. And the reason, like you've seen entropy, containers, and statistical physics. Like, I don't know any proof using any of these methods to prove anything, like an asymptotic formula for like that one, for the number of graphs with a given degree sequence. And what I think the reason is that it's just like putting these local constraints on the vertices, like to have exactly some fixed degree, destroys all kind of independence. It's like it destroys positive correlation, what is used in some of the proofs. Like, so I don't know any proof that uses any of the other methods for the number of deregular graphs. Okay, any questions? Good. So the plan for today is to cover the configuration model and Bolobash's proof. Okay. Good, so what's the configuration model? Okay, so assume that like D and N are integers and that D of N is even. Okay. Well, why do I want D of N to D times N to be even? Yes, exactly. That's 2 times the number of edges in a graph, which is deregular. Yep. So so it better be even for there to be such a graph. Okay. So if D times N is even, what I want to do, I have n cells, C1 up to Cn, and these are pairwise disjoint. Okay. And each of these CIs has size D. So the way to think about this is like if some boxes, 6, and each of these has like their individual their private members. Here D is 3. Okay. And let's say C1, C2, and so on. Here we see C6. And then a configuration is just a perfect matching on these D times N points, right? Is a perfect matching. Let's call this P equals P, which depends on N and D, on these D times N points. Okay, so let's say we start with some perfect matching. One of them is not, here. Right, so just some perfect matching of these 3 times 6 points. And then once we are given a perfect matching, we can form a multigraph, okay? So we form a multigraph G of this perfect matching, which is just we contract all of these cells, and we keep all the edges, including loops and multiple edges. So what we get is a graph with exactly like n vertices, and then, well, this one would give me a loop at vertex 1. It would give me an edge here, here. It would give me a double edge between these two vertices, a single edge here, another double edge here, and an edge here. Okay? So far, this is a multigraph. But if it's not a multigraph, if it doesn't contain any loop or any double edge, then it's a deregular graph. Okay. Okay, so by the way, yeah. So in the graph world, this is just for words, and we use like vertices, edges, and perfect matchings. And just to not to confuse ourselves in the configuration world, we use points, pairs, and configurations for the same things. Okay. So, right. So what I said, so if G of P is simple, then this is a deregular graph. Okay. Now, the observation, one of the crucial observations is that given a deregular graph, in how many ways can I obtain that deregular graph from a configuration? So given a deregular graph, regular graph G on n vertices, how many pairings are there that give me exactly this graph? So G is equal to the graph of a pairing for exactly, well, start with a graph, not this one, but with a regular one, and look at one pairing that gives you that graph. Now I can just permute all the points in one cell, and I can do this for every cell, and that would give me exactly the same graph. Okay? So this is exactly for d factorial to the n pairings. Okay, so what that means is that if I only concentrate on those pairings that are simple, so where G of P is a simple graph, then this is like gives me exactly the same number for every deregular graph. So if I condition, so if I pick P uniformly at random from all perfect matchings from all configurations, so all perfect matchings on these d times n points, then and I condition on the event simple, which means that G of P is simple. And then this gives me like a uniform distribution. Then the G of P, the resulting G of P, is a uniform distribution on the number of deregular graphs. Okay, so in other words, if I want to count my G of ND, then what I do is I take the number of all pairings, but I restrict to those that give me a simple graph times the probability of simple, and this is over a uniform random pairing. And then I'm overcounting every d-regular graph exactly that many times. So divided by d factorial to the n. Okay? So in other words, getting an approximation for g of nd is equivalent to getting me an approximation for the probability that a random pairing gives you a simple graph. Okay, luckily, we already warmed up ourselves. We know how many pairings there are, right? Because we just did the number of perfect matchings. So that's equivalent to g of nd is equal to n times d factorial over n times d over 2 factorial times 2 to the nd on 2. That's the number of all pairings. The d factorial to the n times the probability of simple. Okay. Any questions so far? Good. Now, right. One note about when I want to pick my pairing uniformly at random. There's a very cheap way how I can do this, right? A uniform pairing, how can I generate that? I could start with an arbitrary point and pick pick its neighbor uniformly at random from the remaining d times n minus 1 points. Okay, so pick one edge or one pair at a time. Okay, so here are your d times n points. You start with your arbitrary first vertex. You pick its neighbor somewhere among the d times n points uniformly at random. Now you remove those two from your horizon, and you pick the next one and keep going. So it's a very cheap way to generate this random matching. And with this viewpoint, the following is not too hard to prove. It's a lemma. For any k is fixed. And let's say we have 2k fixed points, yk. They are distinct points. In your universe. So let's call this V, the union of all the cells. Then the probability that xi, yi is in your random pairing for all I can write out a formula for this. And the formula is just the product of 1 over nd minus, well, let me start I equals 0 up to k minus 1, I minus 1 minus 2i. Okay, so for example, this says that the probability that one fixed edge is in my random pairing is exactly 1 over nd minus 1. So this just generalizes this idea that start with your x and pick its neighbor uniformly at random among these n times d minus 1. Okay, so this is an exercise to write out the details today. And now with this idea, we can find we can now say what this probability of simple is. Okay, and that's the theorem by Bolobash from 1983. And it says for D greater or equal than 3 fixed. Fixed. The probability of simple is equal to e to the minus d squared minus 1 on 4 plus times 1 plus little of 1. Okay? Okay. Just what I might do sometimes is that I will write this as e to the minus d squared minus 1 on 4, and I'll put the little of 1 in the exponent. Right, because e to the little of 1 is 1 plus little of 1. No? Okay. So those are two different ways to write the same things. Okay, if I see here an e to the minus something, why should we expect a formula like that? So let's think about like what makes our pairing not simple. So proof sketch. So what makes our pairing not simple is x1. That's the number of pairs that create loops in G of P, and x2 is the number of pairs of pairs that create, let me just say, a double edge. Right, so x1, this is like if I have here some CI, then x1 just counts all those pairs that are in my perfect matching, which would give me a loop edge. And x2 counts all of those pairs of 2 pairs that would give me a double edge. Okay, so these are the number of bad events, counts of bad events. Now, what could I say about any single bad event? So the probability that one of these pairs is there is tiny. It's 1 over nd, essentially. And the probability that one fixed pair is there is 1 over nd squared. So what I'm counting here is like a lot of events. Every single one has a tiny probability, like vanishing probability of happening. And any 2 of them are sort of almost independent. So if I have like a double edge here, that should not like interfere much with like another pair over here that also gives me a double edge over there. So what I expect x1 and x2 to do is that x1 plus x2, they should be, or let's say x1 and x2, they should converge to some, let me write it like this, to 2 independent Poisson random variables. So to a Poisson random variable of some lambda 1 and a Poisson of lambda 2, and these are independent. Okay, that's the heuristic. Now let's see why something like that should be true, or at least give me, Yeah.
Do you have the upper bound on MD?
Fixed, yeah, sorry, I said it, but I didn't write it. Fixed, so you fix it, and this only depends on n. Yes. Any other question? Okay. So for the so if this is true, right? Then okay. What do I want to say? I want to say that my probability of simple, well, with these 2 random variables, that's exactly equal to the probability that x1 is equal to 0 and the probability x2 is equal to 0. Yeah, that's equal. That's just like, because that's a count of the number of bad events. Now, if these two random variables are asymptotically equal to two independent Poissons, then this should tend to the probability that my Poisson of lambda 1 is equal to 0 times the probability of Poisson of lambda 2 to be equal to 0. And we know what the probability of that is. That's e to the minus lambda 1 minus lambda 2. Now, what are lambda 1 and lambda 2? Lambda 1 should be roughly equal to the expected number of loop pairs, and lambda 2 should be roughly equal to the expected number of pairs of double edges. Pairs of pairs that give me one double edge, sorry. Okay, so let's calculate the expectation. What's the expected number of x1? Let me just check my time. Yeah. Wait, I have 20 more minutes, right? Yeah. Good. Okay. So what's the expectation of x1? So I have my n times d boxes. Now, how many possible loop pairs are there? So n ways to choose the cell. How many ways do I have in every cell? We are d-regular, nothing. Okay, so these all have size d. How many possible pairs are there in one cell? It's a d choose 2. And then what is the probability of one specific edge being there? Well, that's our lemma here. That's 1 over nd minus 1. Okay? So what is that equal to? The nd minus 1. Oh, so, okay. That's an n times a d minus 1 over 2. And then I pull out the n times d. And then I write this 1 minus 1 over nd as a 1 plus big O 1 over nd. Okay, so what I'm doing here, and that will happen a lot, is 1 over 1 minus x is 1 plus big O of x for error terms. Okay. Well, and that is d minus 1 on 2 plus little o 1. And this will be my lambda 1. Okay? And now we do the same thing for x2. So let's see. Okay, I removed. So in how many ways can I pick two pairs that would give me a double edge? So I first choose two distinct cells. That's an n choose 2. Then once I have fixed these two cells, I need to pick two distinct points in here and two distinct points in here. So that's a d choose 2 squared. But so now I have picked this pair and I have picked this pair. And then there are two pairs, like two pairs of pairs, to give me a double edge. So I could do these two, or I could do the ones going across. So I have to do a times 2 here. And then, so that is fixing me my number of pairs that would give me a double edge. And then times the probability that both of these edges are there. And that's, again, this lemma. So it's a 1 over nd minus 1 for the first one, and a 1 over nd minus 3 for the second one. Okay, and then here again, I pull out the 1 plus big O of 1 over nd. So that's roughly equal to an n squared over 2. d squared d minus 1 squared over 2 times 2, and then a 1 over nd squared. I make this mistake every single time. Thank you. And then times a 1 plus, but now, so I remove the n minus 1, so I get a big of 1 over, big of 1 over n, actually. So I can simplify this one to n minus 1, because n goes to infinity, but if d is constant, I cannot take out the d minus 1. Okay. And so that simplifies to, so the n cancels, the d cancels, so it's a d minus 1 squared over 4 plus little o 1, and that is my lambda 2. And if we make the check, let's do the sanity check. So lambda 1 plus lambda 2 is in d minus 1 on 2 plus d minus 1 squared on 4, which is exactly equal to d squared minus 1 over 4. So I do, this exponent here is exactly equal to minus the expected number of bad events. Okay. Now how do we make this precise, that x1 times x2 actually tends to an independent Poisson, two independent Poissons? So that is called the method of moment. Method of moments. Okay. Let me state a lemma. Let me first take a sip of water. Who has seen the method of moments before? Okay, almost none of the students. Good. So the method of moments says the following. This is a, well, yeah. So let k is fixed, and lambda 1 up to lambda k are non-negative reals, also fixed numbers, and assume that you have random variables, x1 up to xk, so fixed number of random variables. And these all have a parameter n. So there are actually, there's a collection of random variables. Just like here. I mean, technically, these have a parameter n because n tends to infinity. So these are non-negative integer random variables. Defined on the same space. Omega n for all n. Okay, now I tried to fit the condition here. So if for each fixed set R1 up to Rk, these are non-negative integers, you have the following condition, and that condition takes a while to digest, and we will digest it together. But let me write it first. So you take the expectation of the falling factor of the product of the falling factorials of these x, I, n. I goes from 1 up to k, and the falling factorial are I. And if you take that expectation And you show that this tends to the product from I equals 1 up to k of the lambda I to the k, to the Ri. Then you can deduce that these random variables are asymptotically independent Poisson random variables. Let me write this out. Okay. Then x1n, xkn are asymptotically independent Poisson random variables with means lambda I. Oh, yeah, lambda I for this. Yeah, okay. Let's digest this one. So what do we see here? That's what's called a joint factorial moment. So you look at, I should say that this x sub j is the falling factorial, x times x minus 1 times x minus j plus 1. So these are falling factorials of length Ri for each xi. And the point is that if these xi's were actually Poisson and independent, then that would be an equal. Right? These are the joint factorial moments of the independent Poissons. And you're using factorials because that's the nice form for Poisson. The normal moments are like something complicated polynomials. But for Poisson, the falling factorials, these are the easy ones. And there's something else I wanted to say. Yeah, and the point is that for fixed expectations, lambdas, the Poisson random variables are completely determined by their moments. Good. So that's a lemma, or a theorem, which you can find in chapter 6, for example, of the random graphs by Jansson, Wuchak, Ruchinsky, or chapter 11 in also random graphs by Bolobash. And in the probabilistic method, this is called the Poisson paradigm. Okay, so that's all. I will not prove this. I'll just assume that this is true. But so what Bela actually showed, so the actual proof or remark. So by Bolobash actually showed that in the configuration model, if you have xi to be the number of cycles of length I in this graph G that you get from your random pairing, all of these, and for I at least 1, so yeah, a cycle of length 1 is a loop, and a cycle of length 2 is a double edge. So specifically includes the bad events that we are trying to bound. So these random variables are asymptotically equal, independent Poisson with mean lambda I, which is a d minus 1 to the I over 2I. So we only want that statement for x1 and x2, but like once you figure that out, you get that statement almost for free. I mean, once you figure out what's behind the calculations, you get that. So that immediately gives you something about the distribution of short cycles in a random deregular graph. So you get something more than just enumeration. Okay, but so what we want to do to prove what I just erased, we want to verify this condition just for k equals 2. Verify condition for k equals 2. Okay, so what does that say? So so let R1 and R2, these are any non-negative integers. Okay. Then this one there, what does that say? So we have here the falling factorial of x1, R1, times the falling factorial of x2 of length R2. And we want to know what this is. So let's interpret what's written here, right? So that's the expectation of x1, x1 minus 1, up to x1 minus R1 plus 1, times x2, x2 minus 1, up to x2, x2 minus R2 plus 1. So what does this here, what is the combinatorial interpretation of what's written here? What I'm doing here, I'm choosing R1 distinct loops, right? R1 distinct loop pairs. And I'm choosing here R2 distinct pairs of pairs that give me a double edge. R2 distinct pairs of something that creates a double edge. Okay, so let me sketch that. Yeah, I should have said if you plug in R1 and R2 to be 1 and 0, then you get just ordinary expectation. If you plug in R1, both of them 1, you get like the covariance. And that's just generalizing to all R. Okay. Okay, so what would that expectation be? So now, like we have already, I just deleted. So how many distinct loops are there, loop pairs? We've calculated before that in total, there are n times d choose 2 loop pairs. And now I have to choose R1 distinct ones. So I just do the falling factorial. R1. And the same I do for the number of pairs of edges. That was an n choose 2, a d choose 2 squared, a 2, and that's a falling factorial 2. And now, assuming that all of these, so I now have like my R1 plus 2 times R2 pairs, right? So some of them give me loops, R1, and some others, these total are 2 pairs of pairs that give me a double edge. Suppose that all of them are distinct, then the probability that all of them are there is roughly equal to 1 over nd to however many there are, R1 plus 2R2 plus the sum over all those where they intersect. All those bad events that intersect. So this one, I put as an exercise to show that this is little of 1. So we can do this together later. But for the first one, let's just see. This is roughly equal to n times d minus 1. How often do I see this? R1. R1 and R2 are fixed, and n tends to infinity, so I can do this. And then how often do I see that here? Well, n I see twice. There's an n squared. And a d times d minus 1 I also see twice. So this is plus a 2, R2. And now I need to look at my 2's. So that's a 2 to the R1 from here. And if you look there, then this is also gives you a 2R2. OK? Plus little of 1. And that is equal to, well, calculation, lambda 1 to the R1 times lambda 2 to the R2. OK? Like, I mean, yes. So yeah, let's remember lambda 1 was d minus 1 on 2, and lambda 2 was d minus 1 squared on 4. OK? And that's exactly what I want to show here. So, so asymptotically, this weird expression here is equal to lambda 1 to the R1 times lambda 2 to the R. Sorry? Oh, yeah, I'm missing the probability. Yes, thank you. Times 1 over nd to the R1 plus 2R2. OK, plus little o 1. Yes, so the n's cancels, the d cancels, and all that remains is a d minus 1 over 2 to R1 plus 2 times R2. OK. OK, so that with the method of moments implies exactly what we wanted, that the probability of x1 is equal to 0 is equal to x2 is roughly equal to the probability that two independent Poissons are equal to 0. So e to the minus lambda 1 minus lambda 2 plus little o 1. And this, we said before, is exactly e to the minus d squared minus 4, minus 1 on 4. OK, let me stop here. Yeah, so that's the method of moments. It's a very useful tool for events that are very rare and almost independent. OK, and that's how you get your first formula of the number of d regular graphs when d is fixed. And that's where we will continue.